Have you ever been on an airplane? Well, I'm going to take you on a trip to find out the physics and science behind airplanes. We use them mainly from getting from place to place or to ship cargo and goods to another country or city for trading, manufacturing, or selling. And to fly an airplane, you need to first build an airplane. You think the way airplanes are built is simple. Airplanes have wings, motors, and propellers, but no, in fact, they have more to their designs. Let's start with the history of airplanes. I'll give you a hint at who invented the first successful airplane, although you probably don't need any help. Here's your hint. Flying feels so right. That's right, the Wright brothers. Their first successful airplane consisted of a pretty simplistic design. It had wingtips, rudders, a motor, elevators, fuselage, and of course propellers. But those were the old airplanes. Our next destination will be a more successful one. And as soon as those airplanes were built, new, better designs came flying in. Things were really starting to look up. Okay, so the new airplanes had a different, better appearance and functionality. These airplanes are a lot more sophisticated. Be prepared for a brain explosion. The airplane had six main parts: fuselage, wings, stabilizer or tailplane, rudder, one or more engines, and landing gear. The fuselage is the main body of the machine, customarily streamlined in form. It usually contains control equipment and space for passengers and cargo. The wings are the main supporting surfaces. Modern airplanes are monoplanes, airplanes with one wing, and maybe high wing, mid wing, or low wing, related to the bottom of the fuselage. At the trailing edge of the wings are actually hinged surfaces known as ailerons that are used to gain lateral control and to turn the airplane. The lift of an airplane, or the force that supports it in flight, is basically the result of the direct action of the air against the surfaces of the wings, which causes air to be accelerated downward. The lift varies with the speed, there being a minimum speed at which flight can be maintained. This is known as the stall speed. Because speed is so important to maintain lift, objects such as fuel tanks and engines that are carried outside the fuselage are enclosed in structures called nacelles, or pods, to reduce air drag, the retarding force of the air as the airplane moves. Directional stability is provided by the tail fin, a fixed vertical airfoil at the rear of the plane. The stabilizer or tailplane is a mixed horizontal airfoil at the rear of the airplane used to suppress undesired pitchy motions. To the rear of the stabilizer are usually hinged. The elevators, movable axially surfaces that are used to produce controlled pitching. The rudder, generally at the rear of the tail fin, is a movable axially airfoil that gives the aircraft a yawing turn about a vertical. Directional stability is provided by the tail fin, a fixed vertical airfoil at the rear of the plane. The stabilizer or tailplane is a mixed horizontal airfoil at the rear of the airplane used to suppress undesired pitchy motions. To the rear of the stabilizer are usually hinged. The elevators, movable axially surfaces that are used to produce controlled pitching. The rudder, generally at the rear of the tail fin, is a movable axially airfoil that gives the aircraft a yawing turn about a vertical axis movement in normal flight. The rear array of airfoils is called the empennage, or tail assembly. Some aircraft have additional flaps near the ailerons that can be lowered during takeoff and landing to augment lift at the cost of increased drag. On some airplanes, hinge controls are replaced or assisted by spoilers, which are ridges that can be made to project from airfoils. Airplane engines may be classified as driven by propeller, jet, turbojet, or rockets. Most engines originally were of the internal combustion piston-operated type, which may be air or liquid cooled. During and after World War II, duct type and gas turbine engines became increasingly important, and since then, jet combustion has become the main form of power in most commercial and military aircraft. For certain applications, short-haul traffic between small airports, it is desirable to have airplanes capable of operating from a runway of minimum length. Two approaches to the problem have been tried. One, the vertical takeoff and landing (VTOL) approach seeks to produce the craft that takes off and lands like helicopters, but that can fly much faster. The other approach, short takeoff and landing (STOL), seeks to design more conventional aircraft that have reduced runway requirements. The lessened lift associated with slipback and wing designs increases the length of runway needed for takeoff and landing. To keep runway lengths within reasonable limits, the variable sweep or swing wing has been developed. A plane of this type can extend its wings for maximum lift in taking off and landing, and swing them back for travel at high speeds. A proposed variant of the swing wing, in which one wing sweeps to the rear and another forward, produces an arrangement that causes a minimum shock wave at supersonic speeds. It is thought that if this modification were applied to supersonic transport (SST) designs, it would somewhat lessen their objectionable noise levels. No solution has been proposed to lessen their high fuel consumption. However, recent developments in fan jet engines, in which a turbine powers a set of vans that drive air rearward to augment thrust, have made supersonic flight possible at low altitude. Much research has also gone into reducing the noise and air pollution caused by jet engines. We have reached our final destination. Please put on your seatbelts as we descend back to the start. And that's the science and history behind airplanes.